All right, now for the first type of homework problem that you're going to encounter. From Stuart Kokoska, section 9.3, page 683. We're going to start with number 20. I see this bunch of terms. It says, determine whether the series is convergent or divergent. They didn't ask us what it converges to, just whether it converges or diverges, which is often the question that we're most concerned about, as you will see as we go on in this topic. All right, so the first thing that I need to do, I want to come up with a function that matches this sequence, so the series. So what I need to do is come up with an equation for it. So the first thing I need to do is figure out that this is the sum as n equals 1 to infinity. How are you going to express this in terms of n? Well, since it's going up by 4, so you can look at the denominator is a linear sequence that's going up by 4 every time. So it's going to be 4n. And then think, all right, for n equals 1, I need 3. So if I have 4 times 1, that would be 4. So I need to subtract 1. And then if you want, check to make sure that it matches all of them. It does. All right, so that's what the series is. That's what I got to do first on this one. So then the next thing is I observe that this sequence is positive and decreasing. So if I look at the function f of x equals 1 over 4x minus 1, this function is positive, continuous, and decreasing. All right, so the only place this is going to be discontinuous is at x equals 1/4, but since we're starting at x equals 1, so I could say this on 1 to infinity, because there actually is a discontinuous point when x equals 1/4, but that's not in the interval 1 to infinity, so it's not relevant. But we do have to have a function that's positive, continuous, and decreasing on 1 to infinity. All right, then I can just do the integral from 1 to infinity. If you want, pause and figure out this integral. It's not too hard, 4x minus 1 dx. It's good practice. Figure it out. All right, so its limit as b approaches infinity of the integral from 1 to b of 1 over 4x minus 1 dx. So that equals the limit as b approaches infinity of, so can I just do the antiderivative right away? Sure. It's 1/4 ln absolute value of 4x minus 1 from 1 to b. I can observe that these values are all positive for b greater on the interval 1 to b. These values are all positive, so I don't need the absolute value. So I can say, let's just go ahead and pull the 1/4 out. I don't know if that's useful or not, but I did. Limit as b approaches infinity of ln of, I'm going to change this to 4b minus 1 without the absolute value, because b's are all positive anyway. 4b minus 1 is always positive on this interval, is what I mean to say. All right, so we have that limit, and then minus, now when I plug in the 1, I'm going to get 1/4 ln 3. All right, then what I just observe is this limit, since I have an increasing function, ln of 4b minus 1 is always increasing, and as the b approaches infinity, I have ln of 4b minus 1 is going to go like that, so that the values of ln of 4b minus 1 are going to be approaching infinity. So this is infinity. So since I have infinity and then I multiply by 1/4, it's still infinity. If I subtract something, it's still infinity. So that means that this limit is infinity. And so we're not going to say that, you could say that the sum is infinite. That would not be incorrect. But what we normally say is we're going to say this. We're going to say the sum from n equals 1 to infinity. And so watch how I write this, because this is the required justification in AP world. This sum diverges by the integral test. So a lot of times we're going to be back into this world where we have specific phrases that justify certain conclusions. The integral test is really a theorem that we have that concludes that since this integral is divergent, therefore this sum is divergent, right? It's because if the integral does not converge, then the sum does not converge either. All right, so that's number 20. How about number 22? Can we squeeze that in here as well? Sure, we can. Why not? So if we look at number 22. All right, so we have sum from n equals 1 to infinity. So the question is the same, just does it converge or diverge? Square root n plus 4 over n squared. So all you have to do is think, all right, we're going to make it a function. We're going to do integral 1 to infinity. That's it. And then if that converges, the series converges. If it doesn't, it doesn't. You could probably figure this out on your own at this point. But let's go through just one more example. So f of x is going to be equal to square root x plus 4 over x squared. So let's investigate the behavior of integral from 1 to infinity. 1 to infinity of square root x plus 4 over x squared dx. How are you going to do that, huh? How are you going to do that integral? What do you think? Limit as b approaches infinity. We know we're going to do that. Integral 1 to infinity. How am I going to handle this? What you want to do? You want to split it up because the plus sign's in the numerator? What a good idea. So that's square root of x over x squared plus 4 over x squared dx. All right, so we could also say that's the limit as b approaches infinity. Notice how I never get tired of writing limit as b approaches infinity. I do have to make this a b up here, though. But I never get tired of writing that. I don't just get a little, I think I'll leave it off. No. All right, let's put this in terms of things we can integrate. This is going to be x to the negative 3 halves. I hope you can see that algebra 2 fact. Plus, this one's going to be 4x to the negative 2 dx. Now I'm ready to do my antiderivative. So I can say this is limit as b approaches infinity of, let's see, so raise this exponent 1. I'm going to get negative 1/2 divided by negative 1/2. That's the same as multiplying by negative 2. So negative 2x to the negative 1/2. And then this one, raise the exponent 1, I get negative 1, divide by negative 1, so I'm going to have negative 4x to the negative 1, and this is going from 1 to b. Yeah. All right, so now I'm going to have limit as b approaches infinity of, when I wrote this, I broke it up because they're sort of different things. So I'm going to distribute the limit over the things that I'm taking the limit of. So this is going to be negative 2, and I'm going to go ahead and write this x to the negative 1/2 as over the square root, and then I'm plugging in the b, right? And then I'm taking the limit. All right, and then I'm going to do this one separately. So I'm distributing that limit, so I'm going to have limit as b approaches infinity. I'm going to write this again as 4 over x, but I'm substituting the b, so it's 4 over b. All right, and I put the minus signs. I put this minus sign inside and this one outside. I don't know why. I could have put this negative sign outside as well, but I didn't. Doesn't matter. All right, now when I do minus and put in the 1, both these minuses are going to become positive. So I'm going to have plus 2 over the square root of 1 and plus 4 over 1. All right. Okay. So this limit as b approaches infinity. The denominator is increasing without bound. The numerator is bounded. Therefore, this limit is 0. This, as b approaches infinity, the denominator increases without bound. The numerator is bounded. Therefore, the limit is 0. And this is 2, and this is 4. It equals 6. What is significant about the number 6? Nothing. It is absolutely meaningless except for the fact that it's a real number, okay? It's less than infinity, okay? So that is a real number, and so here's what we get to say. So we've just concluded the limit as the integral from 1 to infinity of square root of x plus 4 over x squared dx. We're not concerned with the fact that it equals 6. All we care is that it converges. All right? Now, you won't have to write this as part of your justification, but what you do have to write is the sum from n equals 1 to infinity of square root n plus 4 over n squared converges by the integral test. All right, and that's how you do that chunk of the homework. So the next thing we're going to look at is some specific examples that we've actually looked at before in terms of improper integrals. Now we're going to look at them in terms of series. So that's what's coming up next.